Okay, so let's continue. Okay, so let's go over the topic for ANOVA, many sample ANOVA. So if we wanted to test them many samples, we just use ANOVA. So ANOVA just do some comparison. So let's check some data. So this data just come from this is building data. So plant growth because so let's say so we can get this we can get this data directly. So it's okay, right? And then we have checked the data. So this data is like we have several groups, like group 1, group 2, like and there's so for each group we have the like for group 1 we have weight. So we will check whether the weight related to groups. Okay, so how many groups? So here we don't know. So let's say so we can check whole data, right? All data, or we can have a visual check first. So we can use a box plot. So we want to check whether the weight related to groups. So use this data. And so here the title for this graph, y label, x label, or color. Okay, so we have a check. Okay, so here we have 3 groups. First one, the control group, and then treatment 1, treatment 2. So this is a typical example for medical data. Like we wanted to compare 2 treatments. So we wanted to compare 2 treatments. So we cannot only just compare the 2 treatments. Maybe we need to compare with control ones, like a placebo. We say placebo. Okay. So let's say, but anyway, like here we have 3 groups. So the question is, these 3 groups have a difference. So we can check the mean, like this average. So the question is, oh, those difference is big enough or is significant? So we cannot, from here we cannot check significance. We just have a visual check. So if we want to check significance, so we can use ANOVA. So in R we have ANOVA, so AOV function. This is for ANOVA. ANOVA, this weight, this variable related to group. Okay, so no. Okay, we use AOV function, and so this put the result to here. Okay, and we want to have a check the result. Use a summary. Okay, so this is the result from ANOVA. Okay, so we say we just check this p-value, right? So p-value quite small, so we can say the difference is significant. Different group have different weight. Okay. 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 And so by now we say before we use ANOVA AOV, but by now we find that we also can use linear model, regression model. Okay, so let's check this. LM model, y related to x, data is this data, and we check ANOVA result. So we get the exact same thing, right? We get exact the same thing. So we can say LM linear model is more universal. So by now we can say we don't need AOV. We still can use, we just use LM. Almost the LM can do many things. But we say AOV is foundation. And LM. So we will check later on. We will check what is that difference. How can we convert AOV, AOV on ANOVA to regulation? So before we say those are two totally different topics, ANOVA or regulation. Regulation is check relationship this variable with other this variable, but ANOVA is check whether different group have difference, right? But let's say from our code we can say we can put those things together. We just check whether there's a different group have difference. We just check whether there's a result related to group related to this variable, right? So LM is just this variable related to this variable. What does we say? What does it say? Okay. If we understand this way, so we say let's say we by now we can regard many step question, stat question can be regarded as whether these things, this variable related to this variable, right? Y related to X. So this is very common R code. Even for this box plot, we can also use this, right? Y related to X. Okay. Okay. So we use ANOVA. Use R can easily to conduct ANOVA. But we still need to check those two questions. So what is ANOVA? Okay, because ANOVA is foundation. If test, if values, all those things just come from ANOVA. And the other one is how can we convert ANOVA to regression analysis? So here we just check first question. What is ANOVA? Okay. So for this problem, so let's check this very simple data, artificial data. So let's check here. Let's say suppose we use this we original. So we say we check ANOVA. So ANOVA, what ANOVA means equal analysis of variance, right? Analysis of variance. So this is the name ANOVA come from. Analysis of variance. ANOVA. Okay. So what analysis of variance meanings? We just split variance into parts. So then we can check the changing mainly from this part or from that part, right? So now suppose we have three group 1, group 1, group 2, and group 3. So we want to check whether these three groups have difference. Okay. So let's check this very simple data. The group 1 data is 1, 2, 3. Group 2 is 4, 5, 6. And this is group 3 is 7, 8, 9. Okay. So ANOVA, we believe. So we just check all the changing meant. Put all the data together. So just 1, 2, 3, 4, 5, 6. So we have variance. We have change. So we believe this changing meant come from either this way or this way. Okay. So the changing from this way, we call this as sum of square of group. So the variance at first, what variance is? Variance according to the formula, variance, samples variance equals summation xi minus x bar square over n minus 1, right? So we denote this numerator part is just the sum of square of total, and this n minus 1 just a degree of freedom, right? So ANOVA, we just focus on numerator part. We say those s is t, total values come from the two ways. So let's say, so here, how can find s is t? S is t is we just put all the data together, the data like that. 1, 2, 3, 4, 5, 6, 8, 9, right? So data just like that. So find, so s is t equals this, right? So summation xi minus x bar. So x bar is 5, right? 1, 2, 3, 4, 5, 6, 5. So just the xi minus 5 square. Okay. So we just plug it in here. So this is the 1 minus 5, just 1 minus 5 square plus 2 minus 5 square plus until 9 minus 5 square. So this is just s is t. Okay. So for this number, it's not so hard. We can easily find this. So this equal 4 square plus 3 square plus 2 square, just plus 1 square. Then just repeat, right? So plus 0 square, then 1 square, just like that, right? 0 square, then 1 square, then 2 square. So this just equal 2 times 4 square plus 3 square plus 2 square plus 1 square. So we find this number equal so this is 16, right? Let's see. So 16 plus 9 plus 4 plus 1. So this equals 60. This is 20, 10, 30, right? Okay, so we say s is t equal 60. So we believe these values just come from the two directions, changing from this direction or changing from this direction. So changing from this direction, we assume like in this direction no change. In this direction no change. Only change come from this way. So this means like if we want to guarantee no change, so this number 1, 2, 3, we just replace 1, 2, 3 as a 2, 2, 2. So let's say like so we just like in this direction no change, right? So we replace 1, 2, 3 as a 2, 2, 2, and here just 5, 5, 5. Or we just replace the data by group mean. So in this way, no change. Only change or variance just come from this way, right? Okay. So such s is t. So we can regard the data as 222, 555, 888. Then such s is t is SSG. Okay. Sum of square from group. So use the same formula. Just each number minus average square, right? So this is just equal to, so average still 5. So 2 minus 5 squared plus 2 minus 5 squared. So we have 3 of them. 3, 2 minus 5 squared. So plus 5 minus 5, 5 minus 5. So we have 3 of them. 5 minus 5, which is 0, right? But first why we put this. Then plus 3 times a minus 5, a minus 5 squared. So this is axis t for such data. So this is axis g. So we find this equal 3 times 9, right? 3 times 9, so here 0 plus 3 times 9. Oh, okay, 27, 27, that's 54. Okay. Okay, so this is axis G. So what is axis E? So we just check. Okay, so in this direction, we call this as axis E. Changing from this direction, so values from this direction, so I put it to here. That's just like, let's say, so data, let's say, changing this direction. So data is 1 to 3. So like for this one, we want to find axis t. So this is t. We do not the axis e. So this is just use same formula, right? So summation xi minus x bar square. So in here, x bar is 2, right? For this 3 number 2. So just 1 minus 2 square plus 2 minus 2 square plus 3 minus 2 square. Okay. So for this group, we can find it's just this. Then for this one, we use the same formula. So for this one, average become 5. So 4 minus 5. So it is also we check this. Okay. So 4 minus 5 square plus 5 minus 5 square plus 6 minus 5 square. Okay. And then for this group, 7, 8, 9. So it is the same. So just equals plus. So 7 minus a5 a square plus a minus a square. Each one minus average square, right? So then plus 9 minus a square. So we find this number equal just 101 or 2 101 101. So this equals 6. So we find, yeah, axis t, this is true. Axis t can split, which is 60, right? Can split by axis g in this direction plus in this direction. Okay, so this is 54 plus 6. We say this is true. So this is ANOVA. We say, so in this general result, we say axis t, all values can split these 2 directions. Okay. So now let's go back to, so this is okay. So ANOVA means like, okay. So our question is, let's say like, our question is these 3 have difference? 3 group have difference? So how can we judge this difference? Is big or small? If no difference, we say, if no difference, then in this direction axis G should be small. If axis G is small, then no difference, right? No difference. So the question is, how can we judge this number, small number or big number, right? How can we judge this number is big number, small number? So we need use this. Here we just want to check this big number, small number. So we want to standardize this. Oh, so we divide by SSE. So we say relatively. Oh, we just standardize. And also here we need divide by degree of freedom. Degree of freedom, divide by degree of freedom. So divided by the degree of freedom is just the average, on the average. And we denote this divided by degree of freedom is MS. MS. So M means mean, right? So we call this MSG, and this is MSE. Okay, and we denote this value as F value. Then so this is just standardized. So then we just check just judge this number is big number or small number. Then we need to check F table or F distribution, right? So the story just like we suppose this F distribution. We have this cut point here. So here's 0. Okay. So we put this F star or F value. So how can we say this big? We just check if how can we check this number, the big number, small number? Then we use this like this is the p value, right? P value. We just check this probability, PV. So there's a probability we call p value. So if p value very small, meaning there's F star, there's a cut-off point is quite far away from 0, so we can regard this number is big. So if this number is big, then SSG is big. So if FSG or SSG is big, then we say, oh, they have a difference, right? Okay. Okay, so this is ANOVA. Okay. Okay, so now let's go back to R. Okay. So let's say okay. So let's say here let's say we call this SSE level in this direction the SSE. So some textbook says that, so what E means? E means arrow. E stands for arrow. But some textbooks say, oh, we call this arrow. So it's hard to understand why what arrow means mistake. So why what mistake meanings here? It seems we do not have mistake, right? So some textbook we call this as this is within each group is with each group, and this direction is between group. Okay, use different name. But here we can say like we can say this SSE. We can understand like this way: SSE equal. So we use this to understand what is the SSE. So we try to unify it. So what is SSE? Oh, I have no space here. So put it here. Okay. What is SSE? So SSE is always equal true y observed y minus yi hat square. This is SSE. Okay. So here, so what is yi hat? Is expected data, or the data based on our assumption. So here our assumption, we can say like we assume in this direction no mistake. In this direction no mistakes, we can regard this as our assumption. Okay. Like in this way, no variance. So this is our assumption. So under this assumption, the data should be looks like that, right? So those are yi hat. Okay. So S is E, so equal, let's say original data is 1, 2, 3, right? Original data is 1, 2, 3, like here 4, 5, 6, right? So we just check their difference. So S is their difference. Okay, so S is equal, let's say so equal the 1 minus 2 square, right? Plus support like true data, expected data, 2 minus 2 square, right? 3 minus 2 square, like that. Okay, so this is S. So in this way, we can say, oh, this is S is E. Right? Observed data, true data, and supposed data. Okay. 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 So let's go back to R. Okay. 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 So maybe we can confirm our result. Let's see. Suppose this is we can find ACE. Let's say let's skip this. Yeah. So you can use R to do those calculations. Yeah. Okay. Okay. Maybe so we put this data as, let's say, changing this as a data file, then use ANOVA. Okay, we use AOV, we can get this same result. Okay. Okay, so now let's check it over here. Okay. So what's the difference between LM linear regression model and ANOVA? So here we emphasize ANOVA should use like let's say go back to here, ANOVA y related to x. This one, okay. So this x should be a categorical variable. Okay, should be categorical variable. So this like those means whether there's a y value related to group, group 1, group 2, whether different group have difference. Okay. So here, like suppose we want to conduct ANOVA, AOV. Let's see. No. So at first we say, oh, if we have this, delete this. Otherwise, we always give us trouble, right? So delete them. Then have a check again. So this data is okay. So let's say in order to apply AOV, ANOVA, so y related to x, this x should be catalog of data. So here we cannot put the final related to so only one variable, right? So here we want to find out whether final related to exams, previous exams. So we should change the data format to this way, like data y, like we put final exam, then like then we put those as like exam one, like we say, let's say previous exam, like exam one, so exam two. So let's say we use stack function to change the, let's say, so data file just Excel file, but for data, I put it here. Let's say, so for data, I have no enough space. For data, we have two format. This is my fault. Okay, so maybe I put it here. Data, we can have like a V1, V2, V3, right? So data, right? So the other way is we just put those V1, V2, V3 as like put it together. Just this is Y. Then this data come from index. We say okay from like this from V1, this one from V1, this from V2, like this. We change data file. So for data file we have two format. So we should change this to this way. Then we can say whether this Y related to those index, variable index. Whether so at the first we need to do these things. So in R we can use stack function. So let's say the code B is stack. Use stack. Then have a check. So this means like so this exam score. So this score from exam 1. This from like exam 3. This from final. Like that. So here we want to check whether those 5 exams have a difference or no difference. So we changing those names automatically give us by R. So we want to change the name. We don't like those names, so we use name function. We say the first column is score, second one is exam. Okay, so use this. Okay, so now we can conduct ANOVA. We also can use the box plot. So let's say so we have 5 exams. So we want to check whether they have a difference or whether difficulty level are same or not the same. Okay, so just check this. Now there are 5 exams have a difficulty level different, or it seems the final score is below others. So whether they have a difference. Okay. So we can use ANOVA. Okay, ANOVA. So there's a score related to exam. Use this data, right? Okay. So let's check the result. So we see that here this is result visual check. This give us the basic feeling, but not a formal check. Formal check is from here. So we can find the p value is really big. Okay, so we can say no difference. We cannot say no difference. Their difference is not so significant. Okay. Okay. So this is just like let's say we can conduct ANOVA from original data. So R is designed for original data. But sometimes we have some similar data. Like here we have 3 classes. We just have the similar data. Like class 1, we have 20 students. and the average is 80, and the standard deviation is 5. Right, class 2, we have 25 students. 25 students, and the average is 81, and the standard deviation 6. So class 3, we have 30 students, average 85, and standard deviation is 7. So we have those similar data. So suppose I teach a class 3. So the data give us some information. The data indicate like data have the evidence that like class 3 perform better than other 2 classes, right? So suppose I teach class 3, so I wanted to say my class perform better, significantly better than others. Or among the 3 classes, my class is the best. So can I see that? Okay, so let's conduct let's say I cannot answer this question. We can check this question later on. So here let's check it, just conduct a ANOVA test. So ANOVA test, we just need to find F values and P values and make our decision. So what is the F value? So this F value is most important, right? F value is this formula equal SSG over degree of freedom divided by SSE over degree of freedom, right? So this is F value. So in order to find this F value, we need to check at first check those degree of freedoms. So what is degree of freedom 1? So degree of freedom 1 is we compare 3 groups. So this SSG is we replace the data by like so I get within each group, within each class, no difference, right? This is our assumption. So this looks like in class 1, everyone get 80, 80, 80, 80. Class 2, 81, 81, 81. Class 3, 85, 85, 85. So essentially we have 3 numbers, right? So the degree of freedom is 2. So here you can see why degree of freedom is 4, because we compare 5 exams, right? Exam 1, exam 2, 3, 4, and final. So here the 5, if we compare 5, then degree of freedom is 4. So here if we compare 3 classes, degree of freedom is 2. Okay, so then degree of freedom, so let's say degree of freedom for all, degree of freedom for all is just equal N1 plus N2 plus N3 minus 1, right? So we put this N1, N2 here. Let's say N1, N2, okay. So N2 is 25, and M2 their average is 81, and N3 is 30, okay, and M3 is 85, okay. Okay, so then degree of freedom 2 equal total degree of freedom minus degree of freedom 1, okay. So we have those degree freedoms. So what is SSG? What is SSG? So SSG is just like the data looks like data is 80, 80, 80. So like just x1 just 80, 80, 80. So we just copy this. The class 1, class 2, just almost every where I put into yeah, so this is we just change this into m2 m2. So just like 81, 81, 81. Okay, so we just use this like x2 and then class 3. Okay, class 3. I did this class 3. So just the class 3 is so the students and their average is 85, and so x3 that's repeat n3 m3. Okay, okay, so here maybe so here just x3 just repeat, we just show up. Maybe we don't need this. If we use this, it's okay, right? Okay, so what is SSG? SSG is just data looks like we just like so we say SSG. So we put the x total x, yeah. SSGX, we say SS. We put this like okay. SSGX is just equal x1, x2, x3. Okay. Okay. So SSG is just the SST for those data. So we say SSG equal some square, right? So inside is this just the SSG x minus mean of SSG x. Okay. Okay. So now let's see. So this is SSG. So what is SSE? SSE, we find this. So how can find where is let's say where is standard deviation come from? So standard deviation, so it's a square is variance. So this is variance for class 1, right? So the variance, the numerator part is just the SSE, right? So we say this is SSE equal SSE equal 把它走 here 那个是 SD1 把它走 SD1 equal SD1 is 5, yeah. Okay, so use semicolon. Oh, not this one. I just put that as SD2 is 6, SD3 equals 7. Yeah, okay. So those values is SD squared. So SSE equal SD1 squared. But we just check the numerator part. So we should multiply its degree of freedom. So degree of freedom is n1 minus 1, right? multiply n1 minus 1. So this is S is E for this is the numerator part, this is E for group 1. Then for group 2, we just use the same. Okay. So I just changing a little bit. So I just change S is 2. So change this M2 and SD3. So SD3 squared variance divided by or multiply the degree of freedom is just the numerator part. So this is SSE. Okay, so we have F value. Yeah. Okay. Then P value equal, so 1 minus PF. This F value, cutoff point, F value. Then degree of freedom, df1, df2. Okay. So check is this F value. So we check the P value. So we can make a decision. Okay, whether this three group have difference, right? Or whether we can say group class 3 is better. So let's run that. Okay, and then degree of freedom and those SSG. Okay. Oh, we have some problems. SSG minus mean. Oh, okay, we have some trouble. Yeah. Okay, what's wrong? Or maybe I forget put the parentheses. Yeah. Okay. So let's do again. Oh, this makes sense, right? Okay. So S is D and S is E. We also need to check. Let's say, maybe for ourselves, we need to check S is E whether this number is okay. Oh yes, this is okay. So then F value. Maybe we also can check what is the F value. Okay. Oh, this F value, let's say SSE df2. Let's say maybe we have some trouble. Let's say df. I forgot n1 minus 1. This one is okay. df2. We also can check the df2. What is df2? df2 72. 72 is okay. Yeah. df1 is 2, so this should be F value. df2 is okay. F value is so big, but anyway, so big. Oh, the P value is very, very small, so we can say, oh, our class 85, other class 81, 80, so our class is significantly better than other class, right? Okay. Okay, so this is today's class. Yeah. So today's class we discussed. At first we review for exam, midterm exam, and we just check ANOVA, original ANOVA. So original ANOVA is compare many groups. So we say instead we have one sample problem, two sample problem, many sample problems. So many sample problems use ANOVA. Okay. So this ANOVA is important in statistics. So by now we say ANOVA. We also show us ANOVA. We also can use regulation LM to conduct ANOVA. So what is their difference or what is their relationship? So we will discuss those things next class. Regulation, because this course we do not focus on ANOVA, we focus on regulation analysis, right? So we can regard this is an application for regulation analysis. We use regulation analysis to conduct ANOVA test. Okay. Okay, so we can stop here. So thank you. So see you next class. Okay.